Hello everyone, welcome to CMSC203. New and improved, and by improved I mean not really improved. So, alright. So, I have some good news for everybody. My little tablet just arrived, so I can now write. And so I have this little whiteboarding app. And show us dogs. Yes, there could be dogs barking. Really one dog. Anyway, okay. Can't relate. So, alright. So where do you guys want to start? Do you want to go over the exam, or do you just want to start in on new stuff? And I see that we already have some comments, though none of them are purely mathematical, so... Yes, please. Okay. Well, okay. Alright, so, cool. Everybody wants to do new stuff. So why don't we start with new stuff? And by everybody, I mean the 10 people who commented. I'll probably do some kind of review. Maybe I'll do it in a separate video for the exam. Yeah. Okay. A Portal 2 stream. Yeah, maybe. That's definitely a possibility in the future. Okay. So, today, basically, So today, what we're going to do is mostly going to be from Chapter 9. Let's see if I can write now. There we go. I'm still learning this new thing, so you're going to have to forgive me for this. Okay, so what is Chapter 9 about? Chapter 9 is about counting. And so, what is counting when we're mathematicians? The answer is generally, permutations and combinations. And then there's like a third category, which is the multiplication principle. Okay, so I don't really, I always found the two terms here kind of confusing because they sounded so much alike. So really, I think the first thing that we're going to start in on is probably the multiplication principle. And I think I'll provide a link to this this live board thing. I think we can actually save this as like class notes. Of course, it's going to be my handwriting, so that's mostly bad. So, okay. So what is the multiplication principle, right? It's the different one. It's the one that basically says that if there are, let's say, n ways to do task A, and there are m ways to do task B. And this is not going to surprise the vast majority of you. There are n, or I should say, I guess I already wrote an m, so there are n times m ways to do both. So that's as simple. Yeah, so this is all in Chapter 9. I think there's a textbook. In fact, there is. So let me see if I can pull up which section it is. It is in so technically the multiplication principle is section 9.2. All right. So let us see if I can start a new page. Nice. So let's do some examples. So, for instance, what's a good first example of the multiplication principle? I guess, so let's just do a simple example like this. So let's say that there are 5 types of, say, condiment, and so and then let's say that so we're going to make a burger. And so let's say that there are 2 types of bread, and there are 3 types of, I don't know, veggies. And let's say that you can only have one of each. So then, it may not surprise you to know that there would therefore be 5 times 2 times 3 ways to make the burger. Oh, hello, Ben. Welcome to the fun. We're starting off easy with the multiplication principle. So yeah, here's an example of the simplest kind of multiplication principle you can do. So I guess you can actually compute this. This is a computable number, so that's okay. All right, so let's do another example. So, what now? Maybe let's compute the number of phone numbers in the United States, or the US system. So, so how are we going to do something like this? Well, so first we have to know what are the decisions that we're going to make. So the decisions that we're going to make are basically, what does a phone number look like, right? So basically what I'm going to say is that it has an area code, which is 3 digits. Wow, those were uniform. And a hyphen. So we'll have a digit here, digit here, digit here. Then we'll have the first 3 digits. Then we'll have the last 4 digits. So that's what a phone number looks like, you know. Okay. So how do we compute the total number of these things, right? Well, let's just do the simplest possible case where we assume that the digits can be anything from 0 to 9. And so the question is, how many things are in this set, right? If this is some digit set, then how many things are in this set? And, you know, so it's normally something that tricks people, but since you're all computer scientists, you know that if you run a for loop with, say, range, 10, it's going to start from 0 and go up to 9, which means that there are 10 things, 10 digits, right? Cool. So we have 10 digits is the size of the set. And so now in order to compute the number of total phone numbers, what we can do is each decision is essentially independent. This is a lot like probability. In fact, there are a lot of probabilistic type questions that you can ask when you deal with this kind of stuff. We're just doing some simple counting, and then I was thinking probability would come later. Anyway, so basically, if you are really kind of explicit about it, you can just write out. You can say something like this. You can say there are 10 and so really this is saying, and of course this has to be multiplied. So because this has to be multiplied, what we're going to do is count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so had 2 requests to slow down. We'll see if I can handle that. Okay. So there are 10 of these total digits. Let's see how good I can. Oh, look at that. I should get, I should be a YouTuber now and say everybody like and subscribe for look at that little underbrace, so perfectly drawn. Okay. So there are 10 numbers. There were 10 options for each. So this is 10 to the 10th power. And so that's the total number of phone numbers. Now, of course, you might say, well, most so 10 billion is the total number of phone numbers. The issue with this is, of course, you might say, well, that's not really true because area codes are not explicitly random and not all of them are assigned. Even in every area code, not all of the first 3-digit combinations are assigned. The last 4 digits are somewhat random. So so generally this would give you a 10 to the 4th power. But these are somewhat less than in real life, right? Anyway, but that's a little fun example. Okay, let's do something else. Well, someone's a critic. So, all right. So let's do another example. Let's do license plates. That's always a good one. So, wow, that was actually, maybe I'll just rewrite that to some. Doesn't that make you feel better? I think it does. Except for the. Okay, we're almost there. Literally, I just have you all watching me as I try to. It's like this whole thing is Eric learns technology, right? So someone asked, why do we put 10 in the previous example rather than 9? And the answer is if you count up the number of digits. How many are there, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the 10th digit. All right. So back to license plates. That's correct. It's the number of things in the set, not the like the highest number, something like that. So let's do another example with license plates. So for instance, my license plate has a number, and then 2 letters, and then 4 numbers, like that. And so let's assume that all numbers are legal, except maybe 0 in the first slot. So don't put a 0 in the first slot. I don't know. Does any information actually get divulged if I would tell you my actual license plate? I don't think so, but I don't want to risk it, because then you all look me up. An example with credit card numbers. Yeah, sure. I mean, it's essentially the same, though credit card numbers are similar to phone card numbers in the sense that, or phone numbers that they don't have all the possibilities filled out. But anyway, let's do this example. So the first question is, I do like some of your nicknames. That's all I'm gonna say. Okay. Yeah, that's my only opinion. Okay. So, how many letters are there, right? And you would say, well, if I recall correctly, there are 26 English letters. Or I guess really we should say Roman. Wow, that didn't go as well. And then, okay, and then as we know, there are 10 digits. So, how many possible license plates of this form specifically, right? Of this specific form are there? Now, there's a bunch of, so you can't use the letter O. Do you want to get rid of the letter O? We can get rid of the letter O. Do you want to get rid of the letter I? Because it could be a 1. Does anyone have an I on their license plate? I'm not sure. Anyway, maybe we'll get rid of O and I. So really, let's just do 24. So, there's 10 digits, and let's just say that we're only going to use 24 of the letters. We're definitely putting Q's in, even though I don't care if they're allowed or not. I like Q's. So we're keeping Q. So how many possibilities are there, right? So how many possibilities are there for the first thing? And oh, look. So Abe, you have to give me the like back because I was able to circle this. Look at that expert circling. Okay, so it says Roman, but it doesn't matter what it really says. I was just being pedantic. So let's draw our slots. And so remember that this is a number, but it has the number minus 0, so we can't use 0 here. Here's letters, but we're not going to use O and I. And then here's numbers that we're going to allow to be whatever you want. So here, there are exactly 9 options. And then there are 26 English letters, but we're going to use 24 this time. There we go. Sorry about that. And so if we use a letter, can we repeat the letter? And the answer in this case is yes. But we'll do the next example where we can't do repetitions, and I'll show you how all that works. Okay, so here we get 24 again, and then this is not 9, right? This is 10 because there are 10 digits and there were no restrictions. That word is restrictions. So, cool. So now what we see is that we have 9 times 24 squared times 10 to the 4th. And that's the total number of license plates that we have. Now, I mean, you can say, that this is a slight overestimation or underestimation or whatever, but we don't really care. These are just example problems so that we can kind of learn how to do this kind of multiplication principle stuff. All right, let's do another example. So if you have questions, people, I can read your comments because I have multiple monitors. So I have the comments up on one screen and I have this up on the other screen. That's just so you guys know why I can see your stuff so quickly. All right, so now let's do license plates. And this will lead, no, not license planes. With no repetitions. So the point here is that if you have this say what is it going to be? A number, letter, letter, number, 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 number. So this is a good example. This is a good example because if we don't want repetitions, that means that, for instance, let's say that you have a license plate 3, AZ 2184. This is okay. But if you have the license plate 3BB 2591, that's not okay because we have a repetition. Or if we have the license plate 7 ZQ 1111, this is also not okay. And of course we know that the worst thing in the universe is the lack of okayness. Good question. What if the order got changed? We'll deal with that question as we talk about permutations. So we're about to talk about permutations here anyway, but let me just kind of explain what we're going to do here. So we can do this without actually mentioning the word permutation, even though I've said it 3 times. The reason why we can talk about it without mentioning permutations is because I can always just ask you. I can say, how many ways can I fill in this this box right here? Now, of course, I should erase this whole thing. So how many ways can I fill that in? And the answer is 9. Because remember that there was no 0 there. And so because there's no 0, we have 9 options. And then here, this letter cannot be a digit, so we still have 24 possibilities. But how many possibilities do we have for this letter right here? So now that we say our fundamental axiom is that we can't have any repetitions. That's right. 23. Okay, good. Now, this is actually a hard one. This is something that used to trick all my journalism students. Oh man, I think 23 is just going to be a meme now. But anyway. Oh wow, okay, some people are not being tricked. Why is this 9? Why is it not 8? I like all the people who say 9, and then one person's like, 9? Perfect. The reason is, here's the reason. Yeah, so the thing is that we've already selected one thing from here, so there's 10 total options, and we've already taken one of those options away for this one. Even though this one was 9, this option is still 9. And then how many options are there for the second number? Well, that's finally 8, right? Because this one, there were 9 options because we removed 0. We put 0 back in, so now there's 9 options again instead of 8. Here there's actually 8 options because we have removed 2 things, then we've removed 3 things, then we've removed 4 things. So if you look at this part right here, we have just derived the permutation P9, 4, which means out of 9 options, pick 4. Yeah, so that's one of the more entertaining things you can do. So why is it counting down, right? So it's counting down because you have 10 options, or let's just ignore all of the rest of this stuff for now and just look at these things. Let's say that we start with 9 options. If you start with 9 options and you pick one, and I say you can't repeat, right? No repetitions, then the next thing you can do is you only have 8 things left to choose from, and then 7 things left to choose from, and then 6 things left to choose from, right? So basically every time you make a selection, you have to subtract 1 from the number of selections that you can make, because if you say that I picked the number 2, right? Then this next thing, I can pick 0, 1, 3, all the way up to 9. But how many things are in this set? The answer is there are. So if there were 10 options for the first thing, and now we only have 9 options, right? 9 options left, because we've had to eliminate 2, right? There's no 2 in here. So now there's only 9 options. So say I pick 5 next. So then the next set of options would be 0, 1, 3, 4, 6, 7, 8, 9, like that. And all you don't know here which ones I'm picking, but what you do know is that I have eliminated the 2 and I've eliminated the 5, or I've eliminated a 3 and an 8, or whatever 2 things I picked. Therefore, I've eliminated 2 options, and there are 8 options left, right? 8 left. And that's what we're counting. All right? Cool. All right. Let's see if I can scroll down using this thing. Oh, I can. Okay, cool. So now, I would like to introduce formally, permutations. So a permutation is a selection Yeah, I see people talking about picking things out of bags. That's a good analogy. It's a selection. You can say like out of a set to be a little more mathematical, but really out of a bag. P. Where repetitions are not allowed. But one of the important things about a permutation that distinguishes it from a combination, which we haven't gotten to, is that for a permutation order, order matters. And what do I mean by order matters? So an example is, if I pick, say, 3 numbers, and I say, okay, I'm going to pick 3, 2, 1, and then I'm going to pick 1, 2, 3. These are the same numbers, right? But a different order. Therefore, they are different permutations. So here's a good example, actually. Let's just list out all the permutations of the set. Oops. And then we'll count the number of permutations. So really the more interesting thing than listing them, so listing all permutations is not usually the most interesting thing to do. The other problem with listing permutations is that if you've actually done the calculation, let me actually do the calculation for just a second. Okay, so there were 15,023,232 options in the last example. So this number here, if you multiply this all together, is equal to 15,223,232. So the reason why it's not interesting usually to list out all the permutations is because the gigantic number of permutations that can happen will quickly overwhelm your ability to do anything meaningful. So, okay, so let's list out all the permutations. So the list of permutations from this set are 1, 2, 3. 1, 3, 2. 2, 1, 3. 2, 3, 1. 3, 1, 2. And 3, 2, 1. So there are 6 of them total. And so we see here that there's 6 total permutations of 3 things. And so that's a pretty reasonable number. I could ask you to do this on some kind of exam, though I don't think I will, because your exams have to be take-home and interesting, which is always dangerous to say. So, okay, let's do it again. So let's say that we want all the permutations of It's not 27. It's not 27 because repetitions are not allowed. If repetitions were allowed, then you would have things like 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 1, 1, 2, 2, 1, 2, 3, blah, right? And in that case, there would be 3 times 3 times 3 equals 3 cubed equals 27 total options. Woo. So that's right. It would be 3. Yeah. So it is 3 times 2 times 1. But let's. So yes, let's write that the total number, the number of these things is equal to 6, which is equal to 3 times 2 times 1. Oops. Cool. So now let's list out all the permutations of ABCD. You know, why not? So let's first count, right? So there's 2 things you can do when you're talking about permutations. You can count them out and you can list them. If you're counting them out, this is usually the more mathematical problem. The mathematical problem is always asking, how many are there? The actual listing problem is really just an exercise in your ability to continuously write. And so, how many possible things are there? So we have 4 slots. Now let's say that I pick, so how many choices do I have for this slot? I have 4 choices. Because there are 4 things in this set. So I'll write the number 4 here. So now, if I pick one thing out of this set, let's say I picked C, well then I have 3 choices. Therefore, yes, I see some of you jumping to the answer, which is always fine. And so then let's say that I pick A next. So now I have B and D. And so then I have 2 options left. So I'll pick D. And then I have to pick B, right? That's the one option left. Not just basically. And Michal, you say it correctly. Not just basically. In fact, it is factorials. So really, factorials and permutations in a way are kind of the same thing, because a factorial is just the notation that we use to write down the answer to a permutation problem, right? Factorials are far more useful than just that. There's a lot more applications in factorials than just writing out answers to permutation problems, but I have a feeling like this notation was probably developed to be able to write down things like this. So, okay. So first, so now we've counted them all. So now let's write them all down. So we know that there are 24 of them. So this is why I'm not going to write down, for instance, the number of permutations of A, B, C, D, E, because why doesn't somebody post in the comments what the total number of permutations of this set would be? Let's see, so we got A, B, D, C, and then we have A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. Okay, so that's all the A's. Now let's do the B's. B, A, C, D, B, A, D, C, B, A, nope, that's wrong. I've already got the BA's. B, C, A, D, B, C, D, A, B, D, A, C, B, D, C, A. So well, I haven't told you guys what combinations are yet, and so I will say that, in fact, for the same set, the number of permutations is going to be greater than the number of combinations in general, and I'll show you why in a second. And so here, C, A, B, D, C, A, D, B, C, B, A, D. Oh, C bad. C, B. Okay. C, D, C, D, B, A. And then finally we have the D's. D, A, B, C, dA, CB, dA, nope, dB, AC, dB, CA, DC, AB, and DC, BA. Okay, so if we were brave enough to count all of these, thankfully I've kind of arranged them in groups of 6 each, right? So these are 6, these are 6, this is 6, and that is 6. So, as it turns out, 6 times 4 is 24. Which confirms our earlier estimate of 24. So really the answer is, isn't it better to do this process than to have to list them all out and count them manually? Of course, that's true. Okay. All right, so let's not look at this anymore. So now let's talk about permutations. Where we only take a subset. So you notice that for the previous 2 examples, we did permutations where we were taking every element of the set. For instance, when we permuted 1, 2, 3, we took 1, 2, and 3 each time. When we were permuting A, B, C, D, we took A and B and C and D. What if we had, say, 5 people, let's just say 25 people, in a race? Say it's a marathon. And so if the top 3 get prizes, okay, I must be holding this at a wrong angle because I'm not, there we go. If the top 3 get prizes, then the question is, how many ways can the race end, or be scored, or whatever? Okay, so how many ways can the race end? And so the answer to this is, well, okay, so if the top 3 get prizes, then what that means is that we have 3 slots. And what that really means is that we have, and so how many choices do we have for each slot? So we have 25 people. Now, granted, normally this is not the way that you would think about this calculation, but how many ways can somebody get into first place? The answer is there's 25 people, and we don't know any of the positions yet. So that means that basically anyone can win the, so anyone can win the race. So there's 25 people who can be in first place. And of course you'd say, well, only one of them can actually win, but yes, but we have 25 choices, I should say, for first place person. And then we have 24 choices for the second place. And we have 23 choices for the third place. It's wrong, Alex, but it's not that wrong. You're very close. So what you were trying to do is this. You were trying to say 25 factorial, which of course is the right instinct. You should say, oh, 25, 24, 23. Yep, that's the right way to think about this problem. And you do have to divide. But the permutation formula actually doesn't say divide yet. So it doesn't say divide by 3 factorial. It says to divide by 25 minus 3 quantity factorial. That's right. And I'll say this just out of an abundance of caution. Just remember that 25 minus 3 factorial is not the same thing as 25 factorial minus 3 factorial, or, and it's also not equal to like 25 minus 3 factorial. You can see easily, if you just plug any of these into calculators, why that cannot possibly be true. So so basically, that's why we have to be very careful, and I make sure that the parentheses, the parens are essential. Okay, so then what you see is that this is really 25 factorial over 22 factorial. And let's calculate what that actually is as a number. Not that I'm really terribly interested. But whatever. 13,800. So a lot of times when I'm looking at problems, if people were doing these on paper tests, I would never really look at this number. I would only ever look at their calculations. And let me undo that since I've drawn over the answer. I would only really look at their calculations, because that's really what I care about. I really don't care about if you can plug the number. I mean, I do care about 3% if you can plug the numbers into a calculator correctly. So anyway, okay. So yes, let's continue. Well, this is fun, isn't it? Only 24. If you're not first, you're last. Good one. I like it. New page. So, yeah, so let's just define. So the number of permutations. Oops. The number in a set of size n, where we select, say, most books either use K or R, so I'm just going to use K because I like K. Out of this set, so order matters here is, so you can, some books will use this symbol here, PNK, for out of n things, pick k things. And you can just write that this is equal to n factorial over n minus k factorial. All right, cool. That was not good. Okay, there we go. So, oh yeah, I don't know if I remember saying this in class. I think I did at some point. There's a fun fact. And I say it's fun because it's not really that fun, but whatever. The point is that 0 factorial is defined, so I'll use 3 bars to indicate this is a definition. It's defined to be the number 1. And the reason for that is mainly formulas like this. Formulas like this work even if I say, out of 25 things, pick 0. And now, of course, you can ask yourself, well, how many ways out of 25 objects can I pick 0 of them? And so if 0 factorial was 0, then what you would end up with is 25 factorial over 25 minus 25 factorial, which is equal to 25 factorial, which is gigantinormous, right, over 0 factorial. I guess all of this is exactly the same regardless of what we define 0 factorial to be until you get to this step, right? And at this step you say to yourself, hello, what are you? You're a 0 factorial. So that's a problem, right? If we define 0 factorial to be 0, which is, it's not an invalid thing to do, the only problem with it is that it kind of messes up these formulas, and it would cause, if it was 0, right, if 0 factorial equals 0, then what we would get here is this is like a, does not exist, right? Or undefined, or whatever you want to say, right? So it's some kind of issue. But if we define it to be 1, then the good news is 25 factorial divided by 1 is just equal to whatever 25 factorial is. Oh, you're right. There we go. There. Okay. It should be, but this is the one I wanted. This is the equation that I wanted to generate. So, this is definitely what I wanted to do. So instead of picking nothing, actually what we're doing is we're picking everything, right? So this actually just means pick everything. So, okay, cool. So this is an important fact to remember about factorials, is that 0 factorial is defined to be 1. And the reason why it's defined to be 1 is just because if it's not, then our formulas really just don't work as well. And we would have to have exceptions for every time. It would have to be this formula is true, except for when you arrive at the 0 factorial in the denominator, in which case replace it with a 1, and of course then you would say, hey, wait, why didn't we just define it to be the right thing in the first place? Good question. Okay, so here's another set of, here's essentially an identical example. Let's say that you want, yeah, let's do this. A poker deck, or really a card deck, has how many cards? It has 52 cards. And so they are in 4 suits, each with 13 cards. So, okay, I just have to say that because every time I taught this, I would always ask how many people have played solitaire or poker or any game with cards, and the answer has been decreasing over time. So just wanted to make sure that everybody's happy with this. Okay. So anyway, let's say that we pick a random hand of 5 cards. So say we're playing So if you're picking a random hand of 5 cards, each card, this is the one thing to remember, each card shares, so for instance, the numbers on the cards start from 2, 3, and they go up to 10. and then there's a jack, a queen, a king, and an ace. So as it turns out, there are 13 of these, but each card, because it has its own rank, I guess you would call it, and it has its own suit, it does say 4 suits. So each card is unique. So because each card is unique, we can do this. And so really, it's as easy as just writing down P52, comma 5. And so let's evaluate this. So I'm not usually going to ask you to evaluate it. I just want to do it so that it's in the record, if you know what I mean. It's important to be able to do this, but if you're doing these problems by hand, really the more important thing is to understand why picking a random hand of 5 cards out of 52 cards is P52, comma 5. At least for now. Let's say that the order matters. Let's say that if you picked a card first, you have to keep. You cannot rearrange them. So no rearrangements. Okay, so in this case, it would be 52 factorial over 47 factorial. And, I mean, you can compute the total number here. Let's actually do that. Let's do that for no particular reason. So as it turns out, there are 311,875,200 of these things. So that's a huge number. So okay. All right, so what are some other good permutation problems? Let me, I have to move my pen away from the tablet in order to get control. Okay. So let's talk about permutations with repetitions. So if you notice, the first thing that you see about permutations, at least back in our definition, let's see, where's the definition of permutations? Was it here? I think it was one slide earlier. So, yeah, so repetitions are not allowed. Now, so permutation with repetitions is a different story, right? Because a permutation with repetitions is something where repetitions are allowed. The main thing about a permutation is that order matters. So, let's talk about how we can compute something. Let's say we want to permute the letters in the word what's a good word? It doesn't have any repetitions. Yeah, let's just do many. Yeah, I would do cat, except it's short. So if you have a word, I mean, I guess we can do cat as well. Oh, I know what we can do. Cats. So here's the point. In either of these cases, maple, even better. We'll do maple next. So here is the important thing to see about any of these examples. This is 4 letters, no repetitions. 4 letters, no repetitions. 5 letters, no repetitions, right? So this can be answered with a regular permutation. You can just say, I want to rearrange all of these words. So this is just going to be a P44, which means out of all 4 things, we're going to pick 4 of them and repeat them. So it's going to be 4 factorial over 0 factorial, which is 24. And that's going to be the same thing here. So in both of these cases, this is a P44. There we go. Okay. So in this case, this is a P55, right? And there's not a lot to say about this other than it is 120, or you can say it's 5 factorial over 0 factorial when you do the calculation. So the rule here is that we are only allowed to use the letters that are inside this word. So for instance, the only letters that exist to us here are C, A, T, and S, or M, A, P, L, E, right? So each time we do one of these examples, only those letters exist, and so that's why we're only permuting. If you actually wanted to ask how many letter combinations, that's a decent question. Like if you wanted to ask how many letter combinations are there of just all letters, right? So, or how many letter permutations? Permutations. Well, yes, Michal. So I want to get to that. I just wanted to do some examples of things that didn't have repetitions before we get to the repetitions. So if I wanted to know how many non-repetitions, right? Non-repeating permutations. I wish this thing would come on. How many non-repeating permutations are there of just letters? So, for instance, A to Z. The answer is that's a P26, 4, right? Because we're increasing the number of things that we can select out of. We can select out of 26 now, and we want 4 of them. So that means that we're going to do a 26 factorial over 26 minus 4 factorial. So that's equal to 26 factorial over 22 factorial. The easier way to write that is just, if you realize that all of these things are going to cancel, right? So if we have, say, 26 times 25 times 24 times 23 times 22 all the way down to 1. So that's 26 factorial. And then here in the denominator, what we're going to have is 22 times 21 times 20 all the way down to 1. And so all of these terms, including the ellipses, are going to cancel. And what we're going to be left with is just this thing here, which is 26 times 25 times 24 times 23, which is actually reasonably computable. Okay, so apparently that is equal to 358,800. And as you can see, these answers, the actual computed out answers, are really the least interesting part of all of this. All right, let's do a repetition example. So now, what if we do have repetitions? Hello. And let's say that I want to know how many ways we can permute this. Yeah, how many ways I can permute this, but distinguishably. So you can also call these distinguishable. Permutations. Okay, so thanks for the tech support. I'll look at that later once I figure out my life. Yeah, exactly. Okay, so distinguishable permutations. So we want to know how many ways we can permute this. So if we just wanted to know how many ways we could rearrange HE, say that this was L1 and this is L2. Right? If they were distinguishable, if you could tell L1 from L2, then this would just end up being a 5 factorial. If L1 is not equal to L2. Yeah, so that's a good guess. And the reason why it's a good guess is because it's right. But also, so the question is, why is 5 factorial over 2 factorial the right answer? So why? The answer is because what you do is it's basically this way. You ask how many total permutations are there, 5 factorial, and then you ask yourself how many ways can I permute L1 and L2 now such that they are such that they are now indistinguishable. And the answer is, well, you have two things, and the number of ways that you can permute two things is 2 factorial. So that's right. So you'll end up with 120 divided by 2, because 2 factorial is just 2 times 1, right? And so in this case, we are going to get 60. That's correct. We are determining the number of distinguishable permutations in the word hello. So you know that in the English language, or in most alphabets, there's not actually an L1 and L2, right? There's not two different L's normally. And so I'm just making these two different L's so that we could tell the difference. So if there were 3 L's, it would be 3 factorial. So let's just do another example. What if we had the word enqueuing? E, if I can write an E, U, E, I, N, G. So let's apply the same principle, right? So how many different... So first thing what we have to do is we have to count the number of letters. So we count up the number of letters and we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 total letters here. And now, what are all the repetitions that we have? So what we have is, we have an E, we have an E, and we have an E. So there's 3 E's. I feel like I'm Pat Sajak. Oh, it is good to love the word in queuing. So here are 2 U's. And how many N's are there? There's 1, 2. Yep, so if you could tell all those letters apart, right? Let's say that we had E1, E2, E3, U1, U2, N1, N2, then the answer would just be 10 factorial, and you just go about your life. But we know that there's 3 factorial ways to jumble up the E's, there's 2 factorial ways to jumble up the U's, and there's 2 factorial ways to jumble up the N's. So you're going to have to divide by all of that. Yep. Yep. And in that case, what are we going to end up with? So I'll let all of you think about why this is the kind of right answer as I calculate, because calculation is inherently boring. So what is 10 factorial? 10 factorial, if I'm not wrong, is somewhere around like 3.6 million? Yeah, 3.628 million. Divided by 6, divided by 2, divided by 2. So this number here is 3,628,800. Why do you multiply them? You multiply them because it's the multiplication principle, right? There are 3 factorial ways to jumble up the E's. There are 2 factorial ways to jumble up the U's. Then there's 2 factorial ways to jumble up the N's. And because we are doing all of these activities, right, we're doing all 3 things, this is the multiplication principle. So unfortunately, this thing here is not a P anything anything. And so the actual final answer is apparently the best number in the universe, 151,200. All right. Any other questions or comments about this example? Does everyone like my choice of word? I do. A 17 is the best number in the universe because 17 doesn't matter. So, oh yeah, it does kind of, you're right, it does look a bit Scrabblish. So, let's do one more example. So here's an example where, so let's count the number of total coin flips. If you flip a coin 10 times. And the answer is, well, it's the multiplication principle, right? And instead of writing out 10 slots, I'm just going to write out 1 slot and put a 2 in it. And we know that there are 10 of these slots. So if there's 10 slots, it's not 2 times 10, right? I'm multiplying the number of slots by 10. What's the actual number of total coin flips if you flip a coin 10 times? The number of total different options. And what I mean by different options is something like you get a heads, then a tails, then a heads, and a heads, right? That would be one option. Exactly. So this is, it would be 2 times 2 times 2 times 2 times dot 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 times 2. So it is equal to 2 to the 10th power. So this is a pure multiplication principle example. Now, what if I ask you how many ways can we have 5 heads and 5 tails? So, as it turns out, it's the number of distinguishable permutations of this word I'm sure you've all used this word in your daily lives, but whatever. So you see that, I mean, this isn't really as, this is not a real word, but it's a word in the sense of coin flips. And so how many different ways can we permute these letters, right? And so we know that there's 10 of them total. And what else do we know? We know that there are 5 H's and 5 T's. Right? So in this case, there will be 10 factorial divided by 5 factorial, 5 factorial. And when I don't write anything between the factorials, there's a hidden multiplication. So let me actually do this calculation, and then we can compute. So for instance here, 10 factorial is in fact that 3,628,800 number, but who cares? We divide by 120, and we divide by 120. Nope. Cool. So this number, QED, is it's a word. Sure, I like it. 252. So if you know that this is 1,024, let's say, and you know that the number of ways that you can get 5 heads and 5 tails is 252 in different orders, then, I mean, if you believe that probability exists, this is not a probability unit, but let's just say the probability of, say, 5 heads, right, out of 10 coin flips is going to be equal to 252 divided by 1,024. So actually, the probability of 5 heads and 5 tails is just, I think it's what, just slightly less than a quarter. So it is 0.246. So there, that's pretty close to a quarter. All right. So it is time to end class, I would think. I think that the way, if you guys, I will probably try to release a homework on Wednesday. I will try to get the office hours up and running. So office hours, if you're in 201, 202, then you have seen the Discord office hours. So I will create a Discord chat where you guys can join me, and where you can talk to me and yell at me and ask me questions and that kind of thing. I'll try to have that up and running by Wednesday. So, all right, everyone. Stay safe out there. Nice. Okay. Talk to you guys later.